Afternoon, everybody. Welcome back. I know that you are all anxious to get back to learn some mathematics. I know that I was super anxious to get back to teach some mathematics. But nerds, we're going to be starting chapter 7 today. Yes, it's out of order. I'm aware. The last thing we did before break was ended chapter 3. I know that. Don't worry. We're going to come back to chapters 4 and 5 and 6. They're not going anywhere. This is just the order that the district wanted me to teach it, so it's the order that I'm teaching it. Chapter 7 begins with exponential functions. I know the unit section's called graphing exponential functions, but it's actually graphing exponential functions as well as modeling the real world with exponential functions, which means word problems. Like I said, the first half of the notes today, we're going to get through the graphing portion, and tomorrow we'll get to the word problems. Exponential functions are very real-world mathematics, useful to us in a lot of ways. They're one of the most real-world things that I could teach you, and it's because money, okay, interest is exponential, debt is exponential. Anybody interested in any kind of medicine or biomedical? Bacteria growth is exponential. Viral replication is exponential. Anybody interested in any kind of crime scene investigation? Dead bodies cool down at an exponential rate. Anybody interested in any kind of nuclear stuff? Radioactive decay is exponential. So there are a lot of things in our real world that either grow or decay at an exponential rate. What? It's a gift. So anyway, there are actually two parent exponential functions, and that's why there's two pictures here, okay? Anytime you have x as the exponent, or within the exponent, you're dealing with an exponential function, and that's what separates it from a power function. Power functions are x's that have a known exponent, like a squared graph or a cubic. Exponential functions, the exponent is now unknown. The base, b, would be a known number. See, b for base. So anything that is in the form of a number times a number to the unknown, this is an exponential function. A and b will be real numbers. A and b cannot be 0. Can't be 0. What is that noise? Goodness. So anyway, if a was 0, you would have f of x equals 0, which would clearly not be exponential. It would be a straight line. Same thing if b was 0. It would be f of x equals 0. Straight line, not exponential. However, in order for this thing to be a function, something graphable where you could connect the dots with a smooth curve, the exponential base, b, must be a positive number. But Mr. M, can't I raise negative numbers to powers? You can, but not all of them, and that's the thing here. We need to be able to raise it to any number we want, and a lot of negative numbers will fail when you try to raise them to decimals because you get imaginary solutions. That means you can't connect the dots. But as long as the exponential base is a positive number, you can connect the dots. So there you go. The base is positive. One more rule. The exponential base, b, cannot be the number 1. The reason why is because if b was 1, 1 to every single power would just be 1, and what you would have here is a times 1, which is just a. So once again, you would have a horizontal line. All right? So a can't be negative. B has to be positive. And b can't equal 1. If you care about the vocabulary of it, a is oftentimes called the initial value because if you drop in x equals 0, you get b to the 0, which equals 1, and then you get a. So a lot of times we call that number in front the initial value, but that's typically more for your word problems. Okay. However, that doesn't mean it's not useful information, because if you plug in x equals 0, you're going to be on the y-axis. That's how you would find your y-intercept. Properties that will be true for all parent exponential functions. All parent exponential functions are of this format. They're not shifted, and a is positive. Okay? Now, can they be shifted? Could a be negative? Yes. But what's in this box is properties of all of the parent exponentials. So 2 to the x, 3 to the x, 5 to the x, 1/2 to the x, 2/3 to the x. These are parent exponentials. Okay? These properties hold true for all of them. First and foremost, most important, domain. Domain is all real numbers. Because remember, b is positive. You can raise a positive number to any power you want. You will always get a positive result. And that's why the range is not all real numbers. The range of all of the parent exponential functions is from 0 to infinity. Because b, a positive number, raised to any number you can think of, will always result in a positive number. Could never be negative and will never be 0. And so that's why it goes from 0 to infinity. Continuous at all real numbers, and that's because you can plug in anything you want, and they have no symmetry. They have no symmetry. Okay? All of the parent exponential functions are bounded below, but not above. So does that mean it's always below? No, of course not. Transformations do the same thing to all functions. If you make a negative, these things would flip upside down. They're not parent functions anymore because we've transformed them. But if they flip upside down, now they'd be bounded above. All of the parents are bounded below. There are no local minimums. There are no local maximums. And I know that... Oh, I was going to skip it. So a horizontal asymptote is a line that our graph will get infinitely close to forever. Okay? Y equals 0 is the x-axis. Because, well, you know, you're never going to hit that value. You can get really, really close to it. You can get really close to it. You can get 0.000000001, you know, but you'll never actually hit 0. At least not for exponentials. Because remember, a positive number raised to any number will always result in a positive value, never 0. And lastly, from that box of things that are true for all parent exponential functions, I know these things are steep, but they are not vertical. There are no vertical asymptotes. Sir?
What does it mean whenever it says like bounded below?
Bounded below means there's essentially a floor that it doesn't go through. And bounded above would mean a ceiling it doesn't go through. So if I reflect this thing upside down, now they're bounded above. Okay? And then to just say bounded means above and below, but that doesn't happen to exponentials. So like I said, there's two kinds of parent exponential functions. Exponential growth is what we call anything of the form ab to the x, where a is positive and b is greater than 1. Exponential growth. See, look, it goes up as x gets bigger. Exponential decay occurs when a is positive and the exponential base is between 0 and 1. Because remember, it has to be positive, but it can't be 1. So this is what happens when the base is bigger than 1. This is what happens when the base is between 0 and 1. We've talked about concavity. Both of these things are concave up. They're both concave up. This one is always increasing. Look, remember, if you put your roller coaster right here, and as you go to the right, your car has to ride this graph, it'd be going up and up and up and up and up forever. So this graph is an increasing function. It's increasing on its entire domain. Whereas this one, if you put your roller coaster car there and go to the right, whee, it rolls down this track. And it will never hit this horizontal line, but it will forever and ever and ever get closer and closer and closer. So technically, you're always decreasing. So even though they're both concave up, this one is an increasing graph. This one is a decreasing graph. The end behavior describes what's happening at the far left, so as x approaches negative infinity, and what happens at the far right as x approaches positive infinity. So as the limit as x approaches negative infinity, meaning as x gets more and more negative, my y values are going to get towards 0. They'll never equal it, but limit means goal. The goal would be the 0, trying to get there forever. This one says as x approaches positive infinity. So as I go this way, my y values, well, since they're going up, are headed towards positive infinity, and we would call the exponential base the growth factor. That is important vocabulary. The only thing that's different about this one is, well, it's been reflected over the y-axis, if you want to think of it like that. But what happens is, because it's been reflected over the y-axis, my endings have switched places. So now the limit as x approaches negative infinity, meaning going this way, is when I go up. And the limit as x approaches positive infinity, meaning as I go that way, is when I approach 0. And this time we would call the base the decay factor. Oops. Okay. Not to be confused with a growth or decay rate. Those are for the word problems. This is the factor. Decay factor, growth factor. And I think that's everything in there. Sometimes students want to ask me, well, what if a was negative? What would we call it then? Well, it doesn't get a special name. If a is negative, we could still graph it. They're just reflected over the x-axis. Then we just call it some kind of exponential function. We can no longer say growth. We can no longer say decay. We just say, yep, that's an exponential function. Okay? So the special names are applied to no shifting and a positive a value. Then we could say exponential growth or exponential decay. They're very specific kinds of problems. Everybody cool on the rules? Yeah? Okay. One thing I did want to mention, though. I've said a couple times that you can transform these things. If you shift these graphs up and down, every feature about them would also shift up and down, including what I would say is the most important feature, the asymptote. If you shift these graphs up, these red dotted lines go up too. So even though they're not actually part of the graph, they behave as if they are part of the graph. So if you shift up or down, those lines shift up and down as well. Cool beans? Yes, Mr. Rep. Fantastic. Okay, great. Let's pretend for a moment that you've never seen one of these curves. So we're pretending we never saw this. And I said, hey, I'm telling you, you can draw a curve with 2 to the x. And I said, you got to graph it. Your only option would be to throw x values at it and see what y values you get, plot and connect the dots. So that's what we're going to do. Okay? Do you always need to do this many? No. It's just for this first one, so that way we can really see what's going on. We get purple. Purple feels like a good color for this. Let's see what happens when x is -3. 2 to the -3. If you can dust off the knowledge from before the break, negative exponents move across the fraction bar, so we'll have 1 over 2 to the 3rd, which is 1/8. So this coordinate is going to be at -3, 1 over 8. It's already really close to 0. Two to the -2. Again, negative exponents make things move across their fraction bar. And 2 to the 2 is 4, so this is 1 over 4. Alrighty, so that's a little bit higher up. Not by much, though. Imperceptibly higher because the grid is small and my pen tip is fat. Two to the -1 is 1 over 2 to the 1st, which is just 1/2. So we have -1, 1/2. I should be able to see the difference there. Yeah. See, it's already starting to curve up. Everything to the 0 power is 1, except for 0 to the 0. We don't do that. But 2 to the 0 is 1. 0, 1. Ah, my y-intercept. How about that? Yeah, if you want to find a y-intercept, you always just plug in x equals 0. That's how you find the y-intercept for all functions. Now it gets easy. 2 to the 1, 2 to the 2, 2 to the 3. 2, 4, 8. So 1, 2, 2, 4, and 3, 8. Next one would be 4, 16, but that's way off the grid, so on and so forth. I mean, you could see it goes up pretty darn fast. Exponentials are some of the fastest growing functions that we have in mathematics. They're not the fastest, but they're some of the fastest. Now I'm going to do my best to draw this without hitting the x-axis because I think it's obvious. 2 to any number would always be a positive number. I'm never going to hit the x-axis. So go ahead and throw that dotted line on there, horizontal asymptote. Do my best. There. So even if you'd never seen one before, you could recognize the pattern and then just connect the dots. Awesome. We're going to find the domain, the range, the y-intercept, the asymptote, and the end behavior. On the homework, if you take a peek at the homework numbers 1 and 2, I left you a table for that information. That way you'll know not to skip doing it. Okay? And the space that's next to the table of information, you're going to do work in that space, which I'll show you on the next 2 examples after this one. Let's see. Green feels good. Domain. This is an exponential. Domain of all exponentials is the same. All real numbers. You can raise a positive number to any power you want. Doesn't matter how much you stretch, shrink, shift, or reflect. You can still evaluate every exponential as long as the base is positive. This one's range, you can see from the graph that it approaches the number 0, but it never actually touches it. But then it goes up forever. So from 0 to infinity. That's domain and range. We happen to luck into the y-intercept. In the homework, if you don't just luck into the y-intercept, you're going to have to plug in x equals 0. But we have it. It was at 0, positive 1. Our asymptote must be written as an equation. If you don't write y equals and then the number, you have not given me an asymptote, you've given me a number. The horizontal asymptote is the line y equals 0. And my graph has 2 endings, a left and a right. Left in behavior, that means going this way, so as the x's get more and more negative. So we're allowing x to head towards negative infinity. Let's see what our y values are up to. Well, this blue graph seems to be crashing into that x-axis. So that's its goal. No, it doesn't equal that. I'm aware it'll never get there. Yes, sir.
What does the funny L and M?
That means limit.
Limit?
Yeah, we've seen these before. The limit as x approaches. It's LIM. Limit as x approaches positive infinity of f of x. That means as I go to the right, what are my y values doing? They seem to be climbing up to me. And they'll never come back down. There it is. You notice in the homework I left you 2 boxes for the endings. One is left, one is right. Do you have any questions for me about the general structure? What makes things do what? How do I know how to identify this? Any of that kind of stuff? Yeah.
Just a question about the limit. It'll always be 0 and negative, or just positive infinity?
No.
Or does that limit it because the x? It's like...
So limit as x approaches just means as you go left or as you go right. So as you go left, you're heading towards x equals negative infinity. You'll never get there because, you know, it's not a number, but you'll continue to go for left. This is saying, as I go to the left, my y values are going towards this number. Now, if this graph was upside down, If the graph was upside down as you went left, this graph would be heading towards negative infinity.
And when the x is growing, it'll be.
For here, it'd be heading towards 0 as you went to the right. Yeah, so
Limits go along with the range.
the limits. So if you have a bounded range of some sort, then one of the limits is going to be the bottom and the other limit would be the top, basically. So just look at the graph and let the graph tell you what the end behavior is. I would graph it first and then do the end behavior. What?
Because that's a lot of numbers.
A lot of numbers. Not really.
Double numbers.
Okay. This graph is a transformed version of the one we just plotted. Now, I'm not going to write down the transformations because we've done that plenty of times this year. What we're going to do is discuss the transformations and talk about how that might have affected the graph itself. Because understanding what the graph should look like due to transformations is very powerful. So what do I see? I see two vertical transformations. These are the outside transformations because they are not happening where the x's are. One of them is a multiplication, one of them is an addition. Vertical, outside, same, if you remember Heil Voss. Your vertical transformations, your outside transformations, follow the same order that you expect them to. So they follow PEMDAS. That means I have to say vertical shrink, factor 1/2, shift up 1. So what does a vertical shrink do to a graph? It does this to it. Whee! Okay? It literally pushes all of its y values closer to the x values, or closer to the x-axis, x-axis. So this graph then will scrunch closer to the x-axis. But then it would shift up 1. And that is a really big deal. Because if every single part of the graph shifts up 1, so does its asymptote. So this is always going to be your horizontal asymptote when it comes to exponential functions. You see, the asymptote should have been y equals 0. So if you shift it up 5, now it's at y equals 5. If you shift it down 2, well, now it's at y equals -2. I'm going to go ahead and throw that on my picture. Y equals 1 is here. There. Awesome. Next, before I find more pieces of the graph, what I always do is decide what the graph should look like. I see a positive a value, 1/2, and I see an exponential base that is greater than 1. A positive a value and a base that's greater than 1. So it's going to behave like this one. It's going to go up and to the right because it has a positive base, a base that's larger than 1 and a positive a value. So armed with that knowledge, I can draw a rough image and know that my graph is going to behave like that. I already know the range. There. I know it's always above the dotted line. So the range is from 1 to infinity. See that? Look at that. Just like that. Based on one piece of information and knowing how transformations affect the parent graph. Ta-da! You know the range. Anyway, as far as graphing is concerned, 3 things after you know what it's shaped like. One of them is the asymptote. Next, you ready for these words? You've heard me say them lots of times this year. What makes the inside equal 0? So the question becomes, what is the inside? The inside for every function is where you find the x's. So for this one, the inside is the exponent position. So for exponentials, all inside transformations, all horizontal transformations are going to be happening in the exponent position. somewhere up there. Okay? So we always say, what makes the end side equal 0 for like inflection points of cubics or for the vertex of a quadratic or even the vertex of an absolute value graph? You've heard me say what makes the end side equal 0 lots of times. This time it's an actual coordinate we can find. So we take the inside and we set it equal to 0. Add 2 to both sides. And we know that we're going to have an important coordinate occur at x equals 2. We need to figure out what the y value is there so we can plot that dot. Well, the exponent is now going to be 2 minus 2, which forces the exponent to be 0. We engineered that to happen. We wanted to figure out what was going to make the exponent equal 0. We like exponent of 0 because everything to the 0 power, every positive base to the 0 power is going to be equal to the exact same thing. 1. And that's why we like it. It makes our exponential base disappear, essentially. And you go 1/2 times 1 plus 1. Since we're having to plot this thing, I'm going to write it as a decimal. Gets you 1.5. We are going to have a dot at 2, 1.5. Which is here. Now that is really close to the dotted line. I only need one more dot, knowing that this is the shape. So what do you think would be more beneficial to you? A dot closer to that green dotted line or a dot further away from that green dotted line? Further away. Further away is more beneficial. And the reason why is because we need to know just how steep to draw this curve. So I'm here, and I know I want to get further away. So looking at this, should I go to the left or to the right if I want to get further away? To the right. And that is why I'm going to go to the next x to the right. Yes?
I just got a quick question. Would it even be possible to go to the left? Like 1?
Yeah.
Because, well, it'd be a negative exponent, but it's like
Yeah.
the asymptotes change.
No, you won't, but you still won't go through it. So if you plug in x equals 1, you'll get 1 over 8 plus 1, which is 1.125. So you're still above y equals 1, but it's not going to really tell you much about how steep this thing curves. It'll just be, it would be like this. It's like that. I still don't know how steep to draw it. But I do know if I go to the right, I'm going to see just how fast it leaves this horizontal asymptote. So let's plug that in. Well, 3 minus 2 is 1. That's half of 2 plus 1. That's 2. So this coordinate is now at 3, 2. Still didn't really tell us all that much, did it? If you want more information, just plug in the next x. If you want more. But what I've modeled for you is what I expect to see in your homework. I expect to see you figuring out where the asymptote is, making a decision about the shape, plugging in whatever makes the exponent equal 0, and then either going to the right or going to the left just to get one more dot. I mean, honestly, right there, that's more than enough information to go, yeah, we get it. But because I want a really good picture, I'm just going to say, what happens if I plug in, I don't know, give me an x value to plug in. 6. All right, let's see if I were to plug in 6. 6 minus 2 is 4. 2 to the 4 is 16. Half of 16 is 8. 8 plus 1 is 9. So 6, 9. There you go. You can really see the curvature now. Did we have to? No. I need an asymptote, a shape, and 2 coordinates. That's more than enough. Whoa, go home, curve, you're drunk. There we go. There. Yes, sir.
How do you know it would be going up and to the right?
So how do we know it's up and to the right? So because A is positive and the base is bigger than 1, it's shaped like this with relationship to its asymptote. Now, I can't call it a growth function anymore because it's been shifted, but I know it's still going to behave as an up and to the right as it leaves the asymptote because A is positive and B is bigger than 1. That's how I know. So let's decide on this one's shape. How about that? Before we talk about the asymptote, let's decide on this next one's shape. Uh-oh, A is negative. That's okay. We all, fingers crossed, master transformations, and we know that if you put a negative number on front, that just flips it upside down, right? So let's talk about what it would have looked like if that wasn't negative. So let's pretend for a moment. Let's pretend A was positive and the base was between 0 and 1. If A was positive and the base was between 0 and negative 1, we would have this shape. See? Positive A and a base that's between 0 and 1, right? We'd have this image. Drawing it in pencil because it's not actually there. It would look like that if that was a positive number. But it's not. It's a negative number. So the image that I just drew in pencil needs to be flipped upside down. There we go. So we've decided on the shape based on A and B, the front number and the exponential base. We've decided on our shape. Now, the first structure, that horizontal asymptote. Y equals positive 4. Awesome. Now, I only need 2 coordinates. You could get more if you want, but you only need 2. I say those 2 are what makes the inside, quote unquote, equal 0. Our inside is our exponent position. So we figure out what makes the exponent equal 0. Subtract a 1 from both sides, and you get x equals negative 1. I need to know what the y value is there. So I'm going to plug in x equals negative 1 to my function. Of course, in the exponent position, negative 1 plus 1 is just 0. We wanted that to happen because every positive exponential base to the 0 is going to be equal to the same number. It's always going to be equal to 1. This is going to give me negative 3 times positive 1, which is still negative 3, plus 4. And negative 3 plus 4 is 1. So I have a coordinate to plot at negative 1 comma 1. That is here, negative 1 comma 1. And it is my opinion that the best way to see just how curvy a graph needs to be, just how steep an exponential needs to be, it is my opinion that you get further from the asymptote. So based on this shape, should I go to the left or the right to get further from the asymptote? To the left. So I'm going to go to the next x, which is negative 2. And I'm going to plug it in. Negative 2 plus 1 is negative 1. And you might be thinking, oh my goodness, fractions. But remember what a negative exponent does to a whole fraction. If the entire fraction has the negative exponent, the whole fraction flips over. So now it's negative 3 times positive 2 plus 4. Negative 6 plus 4, which is negative 2. So the other dot that we need is at negative 2 comma negative 2, which is here. If you want more dots, go for it. Plug in x equals 0 if you want to. You're going to get a decimal. I think it looks like it's 2.5. So if you had to do it on the homework, because I think I made you find y-intercepts, you plug in x equals 0, you get, 1/2 to the 1, that's 1/2. Half of 3 is 1.5, but it's negative, so negative 1.5, and negative 1.5 plus 4 is 2.5, so it would be right there. The point is, I know that this thing is going to be going closer to the asymptote that way and further from the asymptote that way. That is good enough. Four things to graph an exponential. And one of those four is just know what its shape is going to look like. That's it. And the shape is based off of is a positive or negative, is the base between 0 and 1 or bigger than 1. There it is. The last example is going to be like your homework questions 3 and 4, where I give you two graphs and tell you that g of x is a transformed version of f of x. So here's f of x, and they're labeled even better in the homework because I put the cute little text bubbles. Here's f of x, here's g of x. And I'm telling you, f of x is 1/2 to the x power. It is the parent exponential decay graph where the base is 1/2. I'm showing you that you can make f of x become g of x using two transformations, a horizontal shift and a vertical shift. Which one of those is easier to do? In my opinion, the vertical shift is the easiest one to do. But how do I know that? How do I recognize that? Because when you vertically shift a graph, all of its things shift as well, including the asymptote. Because the parent exponential decay 1/2 to the x has y equals 0 as its asymptote. But the transformed graph g of x has y equals -2 as its asymptote. So tell me, which direction and how many do I have to shift f of x? Which direction? Down 2 units. So we're going to shift down 2. So if we're shifting down 2, what does that make the value of k? -2. There. So the horizontal shift is a little bit tougher to see. Not remarkably harder, but just a little bit. Here's how you're going to do this. Identify any pretty point on f of x. I don't care which one, just pick one. Someone shout one out to me. Whoa. A bunch of you spoke at exactly the same time. What did you say? 0, 1, and then someone over here said a different one. Somebody said -1 something. Yeah. So we can either use 0, 1, or -1, 2, or even -2, 4. It doesn't matter. Pick any one of the pretty points. Let's go here. And what we're going to do is we're going to see where that point is going to land after this first transformation. So after that first transformation, that thing would have landed 1, 2. It would have been right there. It would have been right here after shifting down 2. But I need it to land on the g of x curve. So which direction and how many? 3 which way? Go left 3. 1, 2, 3. So we've already got down 2. Now we have to shift left 3. What would the transformation look like normally if you said shift left 3? What would you see in your argument? Mm-hmm. Everything that's in the parentheses, please. What would you have normally seen? No, not just plus 3. X plus 3. So we know that the exponent should have said x plus 3. So our x minus h should have said x plus 3, because we all know that x plus 3 means go left 3. If you subtract x from both sides, you get negative h equals 3. So what does h equal? Negative 3. So that's how you solve for h and for k. And the most important information, though, is what is the equation for g of x? It is 1/2 raised to the x plus 3. That gets us our left 3. And minus 2 gets us our down 2. That is the equation for g of x. Nerds, before I throw the paper on here showing off the artwork, are there any questions? Anything I can help with at all? In your homework, just so you know, I'm pretty sure one of them, it might be number 4, I put a vertical stretch on it. So that one will not be a shift. You won't be able to ask yourself, how far up or down do you need to move? You'll have to ask yourself, what would I have to multiply by to make the y values match? Nobody's listening to me anymore because I'm apparently the only nerd left.